Hi, and welcome to the podcast for thermodynamics energy diagrams. So we're going to be taking a look at this basic concept of energy diagrams. And we'll actually take another look at these when we get to kinetics because those will also play an important role. So there are two basic types of energy diagrams. They're going to be ones for exothermic reactions, and if we remember, an exothermic reaction is one that's going to give off heat energy. All right, so we're going to come in here and we're going to take a look at a few things. And let me get a color that you'll be able to see here. Okay, so the first thing is we're going to want to look at the X and Y axis. So the X-axis can either be time or reaction progress. Reaction progress just basically means when you start with reactants until it goes to products. And on the Y-axis we have energy in kilojoules. This can also be energy in calories or it could be energy in joules. It really doesn't matter. Okay, so we're starting here with our reactants because when you start a reaction, you obviously start with reactants. So your reactants are here, and over here you have your products. Okay, and the next thing that we're going to want to label on this graph is going to be the amount of energy required to get the reaction started. And one of the hardest things for students is that you actually never measure the activation energy, or delta H, we'll get to that in a second, from zero. You measure it instead from your starting point, from where your reactants are starting from. So in this case, I know when I draw it, it's a little bit off here, but it should be around 500 over here. That's about 500. Okay, so your activation energy for this particular reaction is going to be from your reactants, and it's the amount of energy you have to put into it up until the top of this curve. So this would be your activation energy. And in this case, we'd be measuring between 500 and 700. So that's going to be our activation energy. I'm just going to write it over here. It's going to be about 200 kilojoules. Oops, KJ. Okay, the next thing that we're going to measure is going to be our delta H. And delta H is the enthalpy of a reaction. That's the heat that's either absorbed or is given off. In this case, heat energy is actually given off because it's a exothermic reaction. So exothermic means to give off. So again, you're never going to measure from zero. You're going to measure from your reactants to your products. So the products are here, reactants are here, so this will be your delta H or your enthalpy. Okay, so we said this up here was about 500 and we're estimating this around here about 200. So your delta H for this case is going to be a negative because it's exothermic, it has to be negative. Oops, and put an equal sign, negative 500, and again kilojoules. We're going to go with kilojoules. The units for energies over here can change. You could have calories, you could have joules. You're still going to get the same. It's going to be the same process. Okay, so those are our important values to write down. Now let's take a look at an endothermic reaction. And again, this is still reaction progress. You're still going from your reactants. So you're starting with your reactants towards your products in the end. And so this would be your, in the middle here would be your intermediates. And so we'll take a look here at our activation energy. So if, remember, we always measure from our, I'll put some little dots here, hold on a second. So we're going to measure from our reactant line, which is about 200, okay? And we're going to measure from there all the way up to the tippy top. And if we look, that's going to be about, we'll say about 700. So in this case, our energy of activation, so we'll label this energy of activation or activation energy, is going to be equal to 500. Your energy of activation always has to be positive, by the way. Kilojoules, okay? And again, just to remember, I gave this example in class, but if the activation energy is the amount of energy you have to put into a reaction. So let's say, for example, combustion reaction. And well, we're going to go back to the previous screen. Combustion reaction obviously is exothermic. even though this reaction is going to produce heat energy, you have to put heat energy or some type of energy into it to get the reaction started. In a combustion reaction, this would be a spark. So even though you have the fuel and you have the oxygen, you can't make the CO2 and the water and release the heat energy unless you put enough energy to get the reaction started. And so that spark, like lighting a flint or lighting a match, is what you need to get that reaction started. Once an exothermic reaction gets started, then it can go on its own and provide its own energy from there. When we look at an endothermic reaction, some of the energy of activation gets recaptured, but some of it gets used to form the products. So it's absorbing some of that heat energy in the end. So all right, so now we'll look at our delta H. Again, we never measure from 0. We measure from our starting line. And we said this was about 200, and then we'll take this one. This one's about over here, so it's about 500. So that's going to be 200. Okay, so 500, that's delta H is equal to, in this case, positive, because it's endothermic, so it's positive delta H, 300 kilojoules. And that's that value right here, delta H. So that means that it's absorbed 300 kilojoules of energy. And that, again, as you're putting the activation energy, some of it is going to get absorbed in that process. Okay, and that is it for energy diagrams.